This video will quickly introduce the binary number system just to allow you to represent numbers using only zeros and ones. Because what we've done up to now is do circuits where we use zeros and ones to indicate false or true or on or off. And what we want to do now is represent numbers using those exact values, 0 or off, or false and true, so that we can use the circuits to perform mathematical operations. So the number system works in a very simple way. I'll try to divide this page into two, where I'll first do decimal and then I'll do binary, so that you can check what the difference between the two are. If I were to give you a number 520, if you think back to your, I'm just going to fix the focus quickly. There we go. If you think back to your basic days in grade 1, this number 520, okay, maybe grade 3, you will understand by just looking at this that you have a positional number representation, meaning that to the left is more significant, it's weightier, and to the right is less weightier. This 0 here really means that you have 0 ones, 2 tens, and 5 100s. And you have, let's say we have a 3 here as well, that's 3 thousands. So in essence what this means is this number represents something that is 0 times 10 to the power 0, 2 times 10 to the power 1, 5 times 10 to the power 2, and then 3 times 10 to the power 3. That's what this number means to us if it's written in decimal. And we work with decimal because we have 10 fingers. That's how humans count. We count up from 0 up to 9 and then we roll over. So each one of these has a representation of 10 to the power something. 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, etc. all the way there. In actual fact, we also have the decimal separator, and that is a 10 to the power minus 1, 10 to the power minus 2 as you go in that direction. But don't worry about that right now. So if we count, that's the one part of it. Then also, if we were to count in decimal, we count number 0. We don't start counting at 0 typically, but I'll write it down there. 1, 2, all the way, 8, 9, and then we run out of symbols to represent these numbers. We run out of ways to represent a weight, to represent a number. What we do is we go into the next order of magnitude of 10. So we'll say after 9 comes 10. So we roll that over. We clear the ones, and now we have 1 10 and 0 ones. And so count up all the way to 19. And when you reach 19, you will say, I've run out of ways to represent this one. I'll roll it over, and it becomes 20. And this way you count up and up and up and up. I'll just do it on this side here. You'll get to 98, get to 99, and then you'll say, hey, I've run out of ways to represent the ones, I've run out of ways to represent the tens, so roll them both over, and that becomes 100. And then you start counting again until you reach 9999. Then you've run out of ways to represent all three, and it becomes 1000. Right. So what I've just shown you, we're going to do in binary now. Now in this system here, we had 10 ways to represent weight, starting with a 0 all the way up to 9. 10 ways to represent a weight with one symbol. If you run out of symbols, we used more symbols to represent the weight. For this here, we call this base 10, or we say this system uses a radix of 10, and Afrikaans that'll be a grondgetal 10, ground number 10. For binary, we only have two values. The numbers can only be 0 or 1. That's all we have. If you run out, you have to use more symbols. So let's just do the bottom half first. So if you were to look at how you count in binary, you would have seen this in our truth tables. If you count in binary, you go 0, 1, and then we're done. You can't use other symbols. We only have 0 and 1. So if you increment this by 1, it rolls over into the next significant bit. Now the question is, what does this mean? In this case, in the decimal case, that meant 110 because we have 10 symbols. In this case, that means 1, 2 because we only have 2 symbols. So this here would be 1 times 2 plus 0 times 1. If you were to write this down here, let's say we have the number 1010. So this is a binary number, and we're using what we call bits for each digit. So this is a digit 3, digit 5, digit 2, digit 0. I call them symbols. Each one of these represents a digit in the decimal system. In the binary system, we call these digits bits, binary bits. So that there would be a 0 times 2 to the power 0. That there would represent 1 times 2 to the power 1. That there would represent 0 times 2 to the power 2. And that there would be 1 times 2 to the power 3. So if you add all of it up, you'd see this is equal to 0, this is equal to 2, this is equal to 0, this is equal to 8. If you add all of it up, it's equal to 10, and the way we denote this, we say it's 10 in decimal. So this, we write the radix down here. 10 in decimal is 1010 in binary. That 2 there means we're only using 2 symbols to represent a number or to represent a weight. We only have 2 symbols at our disposal to build up big numbers, and that there means we have 10. So the number 10 looks like this in binary. Just another example quickly, because this could be confusing. It's all ones and zeros. Let's do the number 7. So if I gave you 1, 1, that there, just pay attention, I'm adding a 0 here. Right, that doesn't change the value. Same as here, if I add a 0 there, it doesn't change the value. And this relates to 1 times 2 to the power 0, which is 1, plus 1 times 2 to the power 2, which is 2. 1 to the 2 to the power 1, which is 2. So I'll just write that out because I made a mistake. 2 to the power 0 times 1, 2 to the power 1, and 2 to the power 2. So it's 1 plus 2 plus 4. That gives us a total of 7. So 7 in decimal is equal to 011 in binary. So let's go back to the counting quickly. What you can see here is 0, 1. I'm just going to add zeros here to make it look a bit more neat. If I add 1 to this, I get 1. If I add 1 to this, I run out of ways to represent the 1s. I run out of ways to represent the 2s. So I need to add more symbols. So I add 1 to represent 4s. So 2 to the power 2. That's the next place in counting. I'm just going to add zeros here just to make it look a bit neater. And that's typically how we write it out in binary as well. So this is 1, 0, 1, 1, 1, 0. You can see we run out of ways to represent the 1, so it rolls over here, and this becomes 0 again. You can see it's exactly the same way you would use in decimal. It's just we only have 2 symbols to represent it. So if I were to just quickly show you, so this is binary. Let's just look at the decimal equivalent. So what does this thing in binary mean in human readable way and in a human understandable radix in decimal? This means 0, this means 1, this means 2. We can check that. It's 0 times 2 to the power 0 plus 1 times 2 to the power 1. That gives you 2. This is 1 to the power 1 times 2 to the power 0 plus 1 times 2 to the power 1, which gives you 3. And you can do all of them in exactly the same way. You can build it up like that. Alright, so that's how this here also shows you how you convert from binary into decimal. So how do you know what this thing that's written down in a binary number system, how does that relate to what we have in a decimal system? What I also want to quickly show you is how do you convert from decimal into binary. So let's just do a quick example. If I have a decimal number 25, say, and I ask you, what is this in binary? I want to give it to a computer to store as zeros and ones. How would I do that? Well, the way you do that is quite simple. You say 25 divided by 2 is equal to 12. This is the result. This is the remainder, and a remainder of 1. 12 divided by 2 gives you 6 with a remainder of 0. 6 divided by 2 gives you 3 with remainder of 0. 3 divided by 2 gives you 1 and a remainder of 1. 1 divided by 2 gives you 0 and a remainder of 1. That's the method that we use until you reach a 0 here. When you've reached a 0, then your binary number is written down here, where this is the most significant bit, this is the least significant bit. And all that means is this is the ones and this is the 2 to the power many. So if you write this number down, I'm going to write it down in that order there. It's 11001. So this is a binary number which we believe represents 25. Let's quickly calculate it. That's 1 times 2 to the power 0 plus 1 times, this is 2 to the power 1, 2 to the power 2, 2 to the power 3, plus 1 times 2 to the power 4. And if you were to calculate this, it's just 1, 8, and this is 16. So if you add all of it together, it's 7 add 16. You don't get the right result. I've made a mistake. Let's just see what I've done. Oh, I'm right, sorry. 8 plus 1 is 9. 9 plus 16 is equal to 25. There we go. So that's how simple it is to convert between the two methods, or the two numbering systems. What I also want to quickly introduce to you is the whole idea of hexadecimal and octal. So hexadecimal and octal, where hexadecimal is used quite a lot, octal is not really used that much. Hexadecimal has as a base or a radix 16, octal has as a base 8. So if you were to consider now, I'm just going to do octal first. If you were to consider that now you have 8 symbols that you can use, then your counting will obviously be 0, 1, 2, 3, all the way up to 7. When you reach 7, you've run out of symbols because you only have 8, 0 to 7. When you add 1 to it, it becomes 1, 0. Count all the way up to, let's make it 1, 9. Just mind, I'm not saying 19 because it's not 19. 19 is a decimal number. It's 1, 9 in octal. So I guess it's 9 octene or whatever you want to call it. So if you add 1 to that, sorry, my mistake, it's actually 17. When you run out of symbols to represent, add 1, it becomes 2, 0. So 1, 7, add 1 becomes 2, 0. And you go all the way up to 77. When you reach 77, you run out of ways to represent it, so it becomes 1, 0, 0. Alright, so your number system, I guess I don't need to go into more detail, but obviously if for 3 digits, the biggest number you can represent is 777. This is 3 digits worth of octal number. If you add 1 to it, it becomes 1, 0, 0, 0, like that. And the way you calculate the value of it is, this means 7 times 8 to the power of 0, 7 times 8 to the power 1, 7 times 8 to the power of 2, and let's just add one number here. Let's make it 277, so that will be 2 times 8 to the power 3. So you can see you can quickly represent quite large numbers, which you can't do in binary. So if you calculate that, you'll get some substantial number. Actually, I'll quickly calculate it. You get 1537 in decimal is what this thing in octal represents. Now, an interesting fact about octal is you can group bits of ones to go between binary and binary and octal. So if you have this binary number 11001, and I tell you I want to convert it to octal, what you should realize by now is, because the biggest number you can represent with octal is 7, and 3 ones in binary is 7 in octal and in decimal, but in octal you should understand that you can make groupings of 3 ones for each symbol in octal. So if I ask you to convert this into octal, you will say make groups of 3 ones. That's a group of 3, and that is equal to the value of 1. And this is 2 ones, so we just need to add a 0 when we make the group. Make a group there, and that is equal to 2. So this would be 21 in octal is this thing in binary. Let's just do another example. 11011. So this is a binary number. I want you to convert it into octal. You would say make groups of 1s. This is a 7. This here is an 8 plus 2. A 4 plus 2 is 6. 1 less than 7. So 67 octal is equal to that in binary. Now hexadecimal, this is the one that we tend to use a lot, is exactly the same as octal. It's just now the base number is 16, and now our groupings of ones in the binary system will be 4 bits. So hexadecimal, it looks like this: A73E. That would be a number in hexadecimal. So let me just say why this is. The reason we have things like E and A in there now is because we count up 0 to 9, and then we run out of symbols if we use decimal. But for hexadecimal, we need more symbols because we want to go up to 15. 0 to 15 gives me 16 symbols. So we start to use the alphanumeric characters. A, which is equal to 10 in decimal. B, which is equal to 11. C, which is equal to 12. D, which is equal to 13. And E, which is equal to 14. And F reaches 15. So as soon as we've counted 0 to 9, the next thing is A, B, C, D, E, then we reach 15, then we run out of symbols, so the next thing would be 10, which obviously is equal to 16 now. So that's the way you count. When you reach FF, which is 255, by the way, if you're interested, when you reach FF and you add 1 to it, it becomes 100, so 256. So the way that we calculate this, if you have to calculate the number, let's say we just do a simple one first. If I tell you this is B and it's in hexadecimal, what you do to calculate that number is you say, well, that's B times 16 to the power 0, and B we know is equal to 11, so that is just equal to 11. Let's just take a bigger number quickly. If I give you the number A2, I tell you that's in hexadecimal and ask you what's it in decimal. Just going to write, this isn't decimal. What is this hexadecimal number's equivalent in decimal? Well, you would say that's 2 times 16 to the 0 plus A times 16 to the 1. But A is equal to 10. So it's 10 times 16, it's 160, 160 plus 2. So it's equal to 162 in decimal. This big number, same thing, that'll be E times 1, which is 16 to the power 0, plus 3 times 16, plus 7 times 16 squared, plus 10 times that A there is 10, and this E we might as well replace with what it is. It's 14. So it's 14 times 1, 3 times 16, 7 times 16 squared, 10 times 16 to the 3, which gives you one massive number. I'll quickly calculate it. It gives you the number 42814, if I'm not mistaken. That's right, 42814. So what you can immediately see is by using very few symbols, we can put up a fancy big number. And that's exactly what we use hexadecimal for. It's a shorthand approach for making big numbers, and especially for making big binary numbers. So let's just consider this quickly. Like we did here, we said to go between octal and binary, you just need to make groups of 3 bits. Now for hexadecimal, you know that in binary 4 bits is equal to 15, and in hexadecimal we're working with 0 to 15. 4 bits is equal to 1 symbol in hexadecimal, that's equal to F. Okay, so if you were to convert between binary and hexadecimal, you need to make groups of 4. So for example, let's use this exact same number. This number here is 110111, in binary, I would ask you, please convert this into hexadecimal. Well, you say, let's group from the right. Group of 4 ones. I need to group these two as well, so I just add zeros here. So it becomes 0, 0, 1, 1, 0, 1, 1, 1. Those 4 bits there represents the number 7. These 4 bits here represents the number 3. You can calculate it. That's 7, that's 3. So this is 37 in hex. So you've reduced the number of digits, if you were, to a very small number, representing the same weight, because we're using more symbols per digit. Let's just use another one with an alphanumeric in it. So if I have 1, 1, 0, 0, 0, 1, 1, let's make it like that, 1, 0, 0, there we go. So if I ask you to convert this binary number into hexadecimal, you'd group those 4, you'd group those 4, and this you would say is equal to 1 plus 2 is 3, 3 plus 8 is 11. Right? What is 11 in hexadecimal? Ooh, let's go and look. 11 in hexadecimal is equal to B. And this here, it's 4 plus 8 is equal to 12. What is 12 in hexadecimal? It's equal to C. So this thing is equal to CB in hexadecimal. And then you can also calculate the equivalent decimal if you wanted to. Right, I hope that makes sense. One thing that I didn't mention is there's a terminology for 4 bits. We call that a nibble. And what we call 8 bits, like that grouping, we call a byte. And you must have heard that quite a lot. So a nibble is 4 bits, and 8 bits is a byte. If you wanted to know 16 bits, we call a word.